Right, so in this video I'm going to briefly introduce the basic ideas that led Einstein to the theory of general relativity. And we'll start with this one, the equivalence principle. So this goes all the way back to Galileo, although Galileo never really wrote it down precisely. But the idea of the equivalence principle is something which has a very long history in physics. And it's something which, once I say what it is, you will probably agree is quite an intuitive statement. Okay. So I'll draw a picture first before I write it, because I think that may be easiest to understand. Suppose that I have some experiment, okay? Experiment number 1. And suppose that I'm doing this experiment on the Earth or somewhere which has an approximately uniform gravitational field, okay? Let's say G is the gravitational field here, okay? And I do the experiment and I take the result. Now suppose that I do a second identical experiment, so I set up exactly the same things, exactly the same apparatus in my experiment, but in this case I don't do it in a gravitational field, I do it in empty space where there is no gravity, according to me, and instead I put this experiment into some kind of rocket ship and I accelerate it with a constant acceleration. Okay, so in this case you accelerate the experiment in the opposite direction to the first case with an acceleration a here. Okay, so the equivalence principle says that the results of these two experiments will be the same. Okay, so I'll draw 3 lines here to show an equivalence. Okay, whatever kind of experiment you have in this first case with uniform gravity, you will always get the same results as you would in this second case where there is no gravity, but instead you're accelerating the experiment with acceleration which is equal in magnitude to the gravitational field, but in the opposite direction. Okay. Right, so let me write that very briefly in words now. Okay. 2 experiments. One at rest in a uniform gravitational field, G, and one in free space. Free space here means there's no gravity. But with a constant acceleration. And these 2 experiments, as long as they are identical, they will show identical results. So it will show the same results. Okay, so that's a statement in word of this equivalence principle. So I should highlight here, these experiments, they do have to be the same experiment, obviously. Identical. Okay, and here this free space, as I said, means that you have no gravity. And they will show the same results. Okay, so hopefully this statement here reminds you of the statement of the principle of relativity that we saw quite a few weeks ago now. It has a very similar feel, right? You have 2 experiments in 2 different situations and you say that the results must be the same. So this is another example of a symmetry in physical law. It's something you can do to an experiment which will not change the results of the experiment, no matter what the experiment is. Okay. This is, like I said, example of a symmetry in physical law. Okay, so that's what the equivalence principle is. But although it had been known about for a long time, Einstein took this principle and he did something very new with it. He was considering, if this principle is true, what effect will gravity have upon the measurements of time? Okay, so I'm not going to go through the whole argument because I want this to be a very brief summary, but I will tell you the result that Einstein found. So Einstein used the equivalence principle. Equivalence principle I will abbreviate to EP, okay, to save writing. And he used this to show the effect which is known as gravitational time dilation. Okay, so what does gravitational time dilation say? It says that the rate at which a clock measures time will depend upon its position in the gravitational field. Okay, and in particular, clocks at a higher gravitational potential will run faster. Okay, so if I describe exactly the situation, I can give you even a simple mathematical formula for what this is. Suppose that I have, say, Earth, so I have some gravitational field here, and let's suppose that I have one clock here which is measuring time t, and I have another clock higher in the gravitational potential, so that means higher up away from the center of the Earth, and this clock is measuring a different time t prime. Okay, so here note that t prime now is not talking about velocity. Both clocks are stationary with respect to the same observer, right? The only difference between t and t prime is now position. T prime is higher than the clock measuring t. Okay. Right. So in this case, each clock has a certain gravitational potential. So we can say that this is phi of, if we say that this is position R1, and up here this is phi, and let's say this is position R2, okay, then gravitational time dilation states the following: the time or change in time dt prime as measured by the clock higher up in the gravitational potential will be approximately equal to 1 plus the change in gravitational potential between the two clocks divided by c squared times the time as measured by the lower clock. Okay, so here delta phi, as you might expect, is just the difference in potential between the two clocks. Okay, and this approximation works provided that this second time in the equation here is not so big. So it's true for changes of gravitational potential much less than c squared. Okay, right. So that is gravitational time dilation, and you'll see because this is 1 plus something here, that says that dt prime is going to be bigger than dt, right? So in other words, this clock up here will measure more time for any fixed interval than the clock down there. Okay. So again, this effect is very small. I'll show you some examples in a minute. But it has been measured both directly and indirectly through a lot of experiments, which I will briefly mention later on in this video. Okay. Okay. Another thing you can see is that here the units are correct. Phi is related to energy by gravitational potential energy is just the mass of the object times the gravitational potential. Okay, so energy has units. Say if we use SI units, joules, mass is kilograms, and phi. Well, here joule is the same as a kilogram meter squared per second squared, which you can see from the formula for kinetic energy. So here, to keep the units the same, the units of phi must be meters squared per second squared. Okay, so therefore it has the same units as c squared, okay, which is a hint to the fact that gravitation here, well, okay, as we'll see next, you can kind of get rid of the gravitational effects by making some sort of transformation of the observer. Okay, so I said that this approximation is true for these fields. So general relativity gives you a formula which is always true, right? Which is exact as far as we can tell, but it's just not easy to write down a simple formula in that case. So the simple formula only works for fields which are weak. It's actually not too difficult to prove. If you look up the Feynman lectures on physics, I think chapter 42 of book 1, which is in one of the recommended texts for this course, Feynman gives a very nice easy proof of this formula here. So you can look at that. I'm not going to do it because, like I say, I want to keep this a brief summary. Okay. And also note that in any situation that you are used to, delta phi over c squared is a very, very small number. Okay. So if we look at a situation on the Earth, suppose here is the Earth, and I have one observer on the surface of the Earth, and then I have a second observer far away as infinity, as we say. So just a long, long way away, so there is basically no gravitational effect on the observer from the Earth. Then you can calculate what this delta phi is in this case, and you get that delta phi is approximately equal to 6.2 times 10 to the 7 meters squared per second squared. Okay, and if you compare this to c squared, c is 3 times 10 to the 8, right? So c squared is 9.0 times 10 to the 16 meters squared per second squared. So therefore the ratio delta phi over c squared is really, really very small indeed. And that again is why you never usually observe this effect. So this is very similar to the effect of time dilation in special relativity. The reason we never usually think about it is just because in order to see time dilation directly, you need to be going very close to the speed of light, or at least relatively close to the speed of light. And we never get anywhere near the speed of light traveling around just on the Earth as we do. Okay. And the same thing is true for this formula here. To really see this gravitational time dilation effect, you need to be in a situation where there are very extreme gravitational fields, and for fields that we're used to, like on the Earth, the effect is absolutely tiny. But it is still measurable, and it has been experimentally measured. Okay. Right, so next what I want to do is talk about how you can use this equivalence principle to basically get rid of the gravity according to a particular observer who is known as the free fall observer. So I think I'll do that on a new piece of paper. Oh, I should have saved that. Never mind. Okay. Oops. Okay, so okay. Right. So if I do the equivalence principle again, it says any experiment you can do in this uniform gravitational field G is equivalent to doing a same experiment in a rocket, where the rocket is accelerating upwards with acceleration a equals minus g. Okay, but instead of doing the experiment, I can consider here having an observer, who I will call my S observer, who is freely falling, as the name suggests. So if the gravitational field has strength g, then this observer is falling down with an acceleration a, which is, I can't call it a because I used that a. Okay, let's just call it a prime for now. Okay, a prime is equal to g. Okay. This is what we mean by a free fall observer. So he's falling at the acceleration, which is due to the gravitational field. And now if we use the equivalence principle to take this over to the case of the rocket, we see that this observer here is in a rocket which is accelerating upwards with acceleration g, but he is accelerating downwards with acceleration g. Okay, so as a result of these two accelerations, they basically cancel each other. Okay, and then in that case, this observer here is at rest in zero gravity. So what this means is you can rephrase the equivalence principle to say an observer who is freely falling in a uniform gravitational field G will experience the same physics as an observer who is stationary in zero gravity. So maybe I should write that. So an observer who is freely falling in a uniform gravitational field is equivalent to an observer who is stationary, who's at rest, let's say, in zero gravity. Okay, so Einstein used this idea to change the definition of what we mean by an inertial observer in a gravitational field. Because when we talked about inertial observers in the context of special relativity, this person who is at rest, i.e. not accelerating in zero gravity, is what we called an inertial observer. Okay, and Einstein said, well, because this observer is equivalent to this freely falling observer in a uniform gravitational field, we should also consider this freely falling observer here to be an inertial observer. So the freely fall observer in a uniform gravity is an inertial observer. Okay, so this is a redefinition of what inertial means. You're no longer just talking about the velocity, but your definition of inertial now depends upon the presence of a gravitational field. Okay. So in this picture, if I have a second observer S prime who is just standing on the Earth, then according to this new definition of inertial, this observer is not inertial. It's this freely falling observer here who is an inertial observer. Okay. So that's fine. What this shows is that you can change an observer perspective going from the S prime observer here to the S observer here. And the S observer basically experiences no gravity, right? he's equivalent to an observer at zero gravity at rest. So this means that if we only had a uniform gravitational field, then in fact we could get rid of that gravitational field. We could change perspective to a free-falling observer who would see no gravity at all. And in this way you can see that gravity in some ways is similar to the kind of fictitious forces like centrifugal force that you get when you are rotating in a rotating reference frame. You get these new forces generated, which are just there because your observer is not an inertial observer. So I should write that, and then we'll move on to the next section. So this suggests gravity is like a fictitious force. I'll explain that in a minute. It's only experienced by non-inertial observers. Okay. So this fictitious force, this is a term which is in common use. There is some controversy about using this term, whether it's a good idea or not. But basically a fictitious force is a force which only exists if you're in a non-inertial reference frame. So the famous example is if you're an observer on some sort of roundabout, so you're rotating around some central point very rapidly, then from the perspective of this accelerating observer, they will experience a force pulling them outwards, away from the center of the roundabout. Okay. So this is known as centrifugal force. And it's an example of one of these fictitious forces. So what this equivalence principle example is showing is that this is also true for gravity. As long as the gravitational field is uniform, we can get rid of the force of gravity just by changing perspective to one of these freely falling observers. Okay. However, the reason that gravity is not fictitious, it's not something you can get rid of entirely, is because gravity is not uniform, right? If you look at the gravitational field around the Earth, then because the Earth is a sphere, it points in different directions at different points on the Earth's surface. As you move away from the Earth, the gravitational field gets weaker, and so on. So therefore, you cannot get rid of gravity completely just by changing perspective into one of these free-falling observers. Okay, so I should write that. Okay, so like I said, if we look at the example of the Earth, here's the Earth. It should be a circle. Still pretty bad. Okay. The gravitational field lines around the Earth, obviously because of the spherical symmetry, they go in straight lines like this. So as I said, you can see the directions are different at different points around the Earth's surface. If I move up to a point up here, the gravitational field is weaker than a point down there. So it's not uniform at all. Okay. So the gravity is really doing something. Okay. We can't just get rid of it by changing observer perspective, because if I take a free-falling observer at this point here, then that will be different from taking a free-falling observer at this point here. Okay. And therefore these observers cannot really be truly inertial observers. Okay. Right, but what you can say is that provided I don't look too far away, the gravitational field approximately looks uniform. The reason we can assume that the gravitational field on the Earth is uniform, in the classical problems you solve in mechanics and so on, is that we don't go very far away, right? If I stay close to the surface of the Earth, just go, say, 100 meters up or down, then there is very little change in the gravitational field. Okay, so as long as I'm doing local measurements, I'm doing an experiment which is only taking in a small part of the space here, then the gravitational field is approximately uniform, and then I can consider this observer here to be an approximately inertial observer. And the same is true at every point in the gravitational field. If I look at this observer here, then as long as I'm doing experiments which are local relative to this observer's position, again, I can use the free-falling frame of reference to ignore gravity. Okay. And again, same is true of this observer here. If I'm doing an experiment locally over here, I can use this observer's free-falling frame of reference to get rid of the gravitational force. Okay. But what I can't do is extend this globally over the whole of space. For example, if I'm doing an experiment here, and I try to use this free-falling observer's frame of reference, then definitely the gravitational force will be visible, right? Because these observers are in different positions in space, and the gravitational field vector is completely different. Okay. So that's what we can and can't do. Provided our experiments are local, and I take a locally free-falling observer, then I can get rid of the gravitational force. Okay, but on a large scale measurement, I can't. If I try to do an experiment which is spanning a region of space where the gravitational field changes significantly, then there is no frame of reference where I can get rid of that gravitational force entirely. Okay, so for local experiments, a locally free-falling observer will observe no gravitational force. But, like I said, you can't do this globally. So if I have long-range experiments, then I will still be able to see the effects of gravity. Okay, so just a couple of examples here to illustrate what I mean. So it's hard to give a precise definition of what I mean by local and long range here. And long range depends upon the rate at which the gravitational field is changing. It basically means that, say, if I consider an experiment going from here to here, then between these 2 points the gravitational field has significantly changed. So that's what we mean by a long range experiment. Whereas if I look at 2 points very close to each other, then the gravitational field is approximately the same, and this is what I call a local experiment. Okay, so like I say, 2 examples of this. Okay, so the first one I wanted to talk about is the International Space Station. So this is orbiting the Earth, and hopefully you've seen some videos from the International Space Station of astronauts inside floating around and doing funny experiments and things. And often these videos will be described as zero gravity, right? As if there's no gravity in this space station. But if you think about it for a minute, calling these videos zero gravity videos is very misleading, because the space station is actually very, very close to the Earth, right? The radius of the Earth is about 6,000 kilometers, so, and the orbit of the space station is just a few hundred kilometers, I believe. So its position is actually very, very close to the Earth's surface. So the gravity on the space station is not very much different from the gravity of an observer on the Earth. So why do we say that this is zero gravity? Well, it's because of the equivalence principle. The International Space Station is in free fall. Okay, it's always falling towards the center of the Earth just by the force of gravity, and this is what makes it go in a circular orbit around the Earth. But because the ISS is in free fall, okay, this is why it looks like, for an observer on the International Space Station, it looks like there is zero gravity. Actually, as I said, the gravity is still quite strong here. The gravitational force is quite strong, but because the International Space Station is in free fall, for an observer inside the space station, it looks like there is no gravity. Okay, so that's an example of here, right? If you're doing local experiments within the International Space Station, then you won't be able to detect the gravity because you're in free fall. Okay, so a second example is the opposite example. What's an example of a long-range experiment you can do where you definitely will detect the effect of gravity? So here, this is not an experiment which has actually been done, but it's one that could be done and would work. Let's suppose that I went very far away from the Earth and I have two astronauts floating up here, some point above the Earth's surface, and I give these astronauts different initial velocities like this, and I just follow their trajectories as they fall back down to the Earth. Yeah, obviously this is not an ethical experiment. And as they fall, I measure the change in the distance between the astronauts. So the separation between these two astronauts is some function d as a function of time as they start to fall towards the Earth. Okay, and if I measure this function d of t, then definitely I will know there is gravity, because if you were to consider the same situation in zero gravity, right? In zero gravity, if the astronauts started moving, they would just keep moving at a constant velocity, right? And therefore the distance measurements you get would be very different. Okay. So by looking at this function d of t, you will be able to see the effect of gravity on these two free-falling observers. But that's because this is a long-range experiment. The trajectories of these two observers go a long way away from each other, and therefore the gravitational field experienced by the two observers is quite different, which is what makes this a long-range experiment. Okay, so in this experiment you can definitely still see the effect of gravity, whereas in an experiment inside the International Space Station you cannot. Right, so that means that in a non-uniform field, these observers cannot really be thought of as inertial observers in the same sense as special relativity, but if you're doing local experiments, then they do appear to be approximately inertial. Right? Like I said, experiments inside the ISS, local experiments, you can't see the gravity, and it looks inertial. So therefore, these observers are called local inertial observers. Okay? They're not inertial on a global sense, but provided you're looking nearby the position of the observer, their observations will appear to be zero gravity, constant velocity, which is what we mean by inertial observers. Okay, so this last thing I write is free fall observers. In non-uniform gravitational fields are called local inertial observers. Sorry about that. I'll write that a bit neater. Okay. So here the local is simply because, as I said, for local experiments they do appear to be inertial, but if you take long-range experiments then you can still see the effects of the gravity. Okay. Right, so I think I'll stop this video here and then record the next one. So the next one is going to all be about curvature. So you probably have heard that the theory of general relativity describes gravity in terms of a curvature. And basically the reason I've been doing all this talking about inertial observers, free-falling observers, local inertial observers, is to show you how this connection to curvature arises. Okay, so I'm going to start the next video just by talking about curved spaces in a general sense, and we'll see how a lot of those ideas from curved spaces apply back to these concepts like the local inertial observers in space-time. And that will give us some clue about how to describe gravity as a geometrical effect.